let's do this thing. So, welcome to 4 Programming Paradigms in 45 minutes. When I proposed this talk, I did not think they would accept it. When I got the acceptance, I'm like, what the heck am I going to do? There are 190 slides in this talk. It's going to be fast. Get ready to hang on. I'm Aja Hammerly. I'm on GitHub as Thagomizer. The code from this talk will be posted later today. I need to do some licensing stuff before I can get it out. I tweet as _Thagomizer. Assuming that the internet and automation work properly, I have tweeted the slides. And that is going to give you a link to www.thagomizer.com, which is my website where I blog, and I also have the slides from most of the talks I've given. Oh, and I like dinosaurs. I work on Google Cloud Platform as a developer advocate. If you have any questions about Google Cloud, Kubernetes, App Engine, BigQuery, all that stuff, you can come ask me. There's also 3 of my colleagues are here. 2 of them are up here right now, and 1 I told to go see a different talk so that he could learn from different people. We're also probably going to do a birds of a feather or a lunchtime thing, so watch my Twitter. We'll announce when we figure out when we're going to do that. And since I work for a very large company, LawyerCat says any code in this talk is copyright Google and licensed Apache v2. So, formalities over. Onward. So this talk is based on a class I took my freshman year of college. We called it CS60, although the actual title was The Introduction to Principles of Computer Science. And unlike a lot of CS majors, this course was very early in the major, and it was a survey of all of computing. We did finite state automata, we did grammars, we did provability and complexity theory, we did formal logic. But about 10-ish, 12-ish weeks of the course was dedicated to learning 4 different programming languages, each of which represented a different paradigm, and solving the same problem in all of them, and solving some problems that were designed for that language. And I learned a lot of stuff from this course. More than any other class I took in my major, this one made me the computer scientist that I am. And the biggest thing I took from this class was abstraction. When I started this class, I knew Java, I knew some Visual Basic and some Basic. But my concepts of things like arrays and conditionals was attached to the syntax for those things. I thought about them in terms of their syntax. And by forcing 4 completely new languages, 3 completely new languages, 4 languages, all in a very short period of time, I was able to move those concepts from being attached to the syntax to actual abstractions in my mind. If you're a philosophy person and you know Plato's allegory of the cave, you kind of have an idea of what I'm trying to get at here. The other thing I took was that I too could be a polyglot. I was always impressed with people who knew a lot of computer languages, but when you learn 3 new languages in 9 weeks and you're able to be productive with them, you realize that once you have the concepts and the abstractions down, the syntax isn't really that hard. And when you're a polyglot, you can point out the similarities between languages. Concepts like conditions and collections and arithmetic and loading and storing things from memory, they show up over and over again in different languages in different ways. And so understanding those at a conceptual level as opposed to I use this syntax for arrays is really helpful. And the other thing it taught me was there are big differences between programming languages. And different languages are good for different things. And I'm hoping that you guys will take some of that out of this 45-minute crash course, where I try to cover what I learned in 18 weeks in 45 minutes, I hope. But don't worry if you can't keep up. This is supposed to talk about ideas, even though there's a lot of code. So when I took the class, our primary example was solving the puzzle Towers of Hanoi with the little rings and the pegs. You have to move the tower from one peg to the other. Explaining the algorithm to do that, and then explaining that in 4 different languages is going to take more time than I have. So we're going to use something much simpler. I'm going to talk about change. And by change, I mean this kind of change. In each language, I'm going to show you how you would calculate the amount of change you would give if you were a cashier working a cash register. So, everyone following? Let's dive straight in. We're going to start with OO. We're at RubyConf, so we're going to use Ruby. I color-coded my slides. Ruby is, of course, red. And we're going to start with something easy. The code gets harder as we go along. It's just how it is today. So let's talk a little bit about OO. Everything in Ruby is an object. Everything. False is an object. False is a singleton, an instance of an object. Nil is an object. Your classes themselves are instances of the object class. Not all OO languages are this pure, but the general idea in OO is that most things, I would prefer all things, are objects. Well, what's an object? An object is a way of encapsulating state and behavior. State is things like fields, attributes, instance variables. What you call them varies a little depending on the language and your particular background. And behavior is what you do with that state, things like methods. Most OO languages, the object is responsible for modifying its own internal state. In Ruby, we call this self. So if I was an object, I could say self.pets equals the array Emma, Nick, and Shy, because those are the names of my cats. Objects have to interact with each other, because an object just sitting there by itself is rather boring. And the way they do that in Ruby is through message passing. If I want to find out the length of an array, I send the message length to an instance of an array object. That object calculates the length of its internal state and then returns that length to me. So when I'm teaching stuff, I normally try to use my own examples. But since we're going super fast today, I'm going to try to use examples that are canonical or commonplace in the literature so that hopefully you can kind of attach this to something you may have seen before, hopefully. And one of the most common examples for OO is the idea of a bank account. So I'm going to build up a bank account object. Well, objects are instances of classes, so class bank account. Bank accounts need to have a balance of some sort, and for a lot of reasons, it's a bad idea to allow folks to monkey with my balance, which is my internal state, so I'm going to store balance as an instance variable, and I'm going to set it to 0 when I initialize the class, or initialize the object. Note, I'm going to talk about money a lot today, and I'm always going to represent money as an integer number of cents. If you are representing money as float in any of your code, come talk to me later and I will teach you about why that is a horrible idea. So, I'm going to take a break for IRB. I can go bankaccount.new and get an account object back. Now, I know since I wrote the code that my balance is 0, but I can't actually see it. So let's write an accessor. So I'm going to have an adder reader because I don't want anyone outside to be able to set the balance. And that's going to return balance. Back to IRB, now I can see my balance. It's 0. So a bank account with a balance of 0 is pretty much useless. So I'm going to add ways to withdraw and deposit money. So deposit's going to increase the balance. Deposit is a message. It takes an amount, and it adds that to the balance. Withdraw is the opposite. It takes an amount and subtracts that from the balance. And you can see from my IRB break here that it works. So I talked about an object having both data and methods before. In this case, the data is the balance, and the methods, or the behavior, are deposit, withdraw, and initialize. And all of these methods modify the internal state of the object, and my IRB process is communicating with them by passing a message like deposit with an amount, and trusting that the object will do the right thing with that data in that message. So some of the strengths of OO. It's really good at modeling what we do in real life. So like I have a chair here. I could have a chair object. It could have an attribute color. It could have behavior, hold me up, those kinds of things. We think about the world through concepts and ideas that very closely align with objects. We don't think about the world as the chair's color is fundamentally separate from what it does. Objects are also reusable. A good way to see this is think about the standard library. Arrays are objects, hashes are objects, strings are objects, and we all reuse them in all different ways because the same types of concepts and objects show up again and again and again in the problems we're trying to solve. And this means I don't have to implement array.length over and over and over. I think objects are easier to test. I can test an object in isolation and test that it modifies its own behavior correctly, and then I can test the seams between the objects when I'm testing my system as a whole. So, on to the motivating example. So I'm going to do the making change algorithm, OO style. Here's the code. So this is like 28-point font, and I don't expect you to be able to read it. So we're going to build this up piece by piece. So I have a class. I'm going to make a class called cash register, because that's what I use to make change. My cash register has a cash drawer. That's the thing that slides out that contains the money. The drawer contains a bunch of different denominations of bills and coins. I have 20s, 10s, 5s, and 1s. And then I have quarters, dimes, nickels, and pennies. If I was doing a more thorough implementation, I could have the amounts of each that I have in addition to the denomination. Here is the method that makes the change. And it's still kind of small, so let's build that up piece by piece too. Here's the method signature. Make change takes an amount owed. This is the amount that the customer owes the store. And it takes the amount the customer gave the cashier, which you'll see frequently referred to as tendered. Not tender love, Aaron. So the first thing I need to do is I need to figure out how much change I have to give the customer. And this is going to be the difference. And to do that, I subtract the owed from the amount tendered. And then I'm going to represent the bills and coins I need to give the customer in the change array. This is going to be the thing that tells the cashier 5 5s, 3 1s, blah, blah, blah. The next thing is I need to figure out which part of the drawer I'm working in. When I've seen people make change, a fair number of people will start at one end, either the smallest or the largest, and move down the drawer and grab the appropriate amount and then move to the next slot and the next slot and the next slot. So I'm going to do that exact process with my array that is my drawer, and I'm going to use I to index where I am in that process. And, you know, it's a loop. While I still have change to give the customer, while difference is greater than 0, I'm going to loop through this thing. So expanding on the loop a little bit, here's the first part. If the difference, the amount I still need to give the customer, is less than the current denomination I'm looking at, the current slot in the drawer I'm looking at, so that would be the case where I have to give the customer $4.50 in change, and I'm currently looking at the 20s. I can't give them a 20. So I need to increase my index and set my denomination to the next smallest thing. Now I'm making an assumption throughout the entire talk today that my change drawer is always sorted largest to smallest. If it isn't, none of these algorithms work. And once I've done that, I can go back to the start of a loop and try again. So the next part is, now this is the case where I'm giving $4.50 in change, but the current thing I'm looking at is $1. I'm going to say, well, that's not bigger, so I can use that one. So I'm going to add it to the list of change I'm giving, and then I'm going to subtract that amount from the amount still owed to the client, or the customer. And then I go back to the top of the loop, and I keep going through this, and eventually, I'm going to have the change I need. And this ends up with this method. So those of you who really like your OO are like, this is not OO, and you are totally right. This is a really, really bad problem for demonstrating OO. And that brings up the point that different programming languages are good for different things. But this is a fine problem for demonstrating the other 3 paradigms I'm going to talk about today, so that's why I used it. This actually looks much better as a functional program. On to our second paradigm. I'm going to use Racket, which is a general-purpose programming language in the Lisp family. Lisp, in turn, if you have never heard of it, is the second oldest multi-purpose high-level programming language. Lisp stands for Lisp Processor. The only language that is older than Lisp is Fortran. And Racket and Lisp are well suited to demonstrate functional languages, although both of them are not limited to that paradigm. You can also use Ruby for functional languages, but 4 languages, 45 minutes. That was the promise of the talk. So, an overview. Functional languages are built of functions. Who would have thought? Functions take in data and output data. I'm going to focus today entirely on pure functional programming, which means that my functions don't ever store state, and they don't ever mutate the incoming data. So if you give me an array, I will give you back a new array. I will not modify the one you gave me. So no bang methods if you're still in a Ruby mindset. A nice thing about pure functional style is the output only depends on the input. It doesn't depend on what came before. So I can do a bunch of stuff and then give the same input, and it will always be the same thing. History doesn't matter at all. And the really fundamental thing of functional languages is that data and procedures, state and behavior, are separate, unlike OO, where they're encapsulated together. I'm hand-waving a bit here. It's not actually entirely true, but for the purposes of this talk, it is true. So for all the languages that aren't Ruby, I get to teach you syntax. The biggest thing you need to know about Lisp family languages, and Racket in particular, is that we're used to things like in Ruby that use infix notation, but Lisp languages and Racket use prefix notation. So to add 3 and 5, I use plus 3, 5. And you're like, well, that's weird, but it's actually super useful because I can do 1 times 2 times 3 using only one times symbol, which I couldn't do in Ruby. Times 1, 2, 3. That multiplies all those together. I'm not limited to just 2 arguments, which you are with infix notation. And you're like, well, that's completely unpractical. How can you do multiple levels of it? Well, the answer is on the last line there. I'm multiplying 3 and 5 and subtracting 6 from 10, and then I'm adding the 2 results together. And you just use multiple levels of parentheses. And I really like this because the order of operations is very, very explicit. So math is not particularly interesting on its own. I need to be able to write my own functions. You declare a function by putting the word define, and then in parentheses, the name of the function and its argument list. The square function takes 1 argument, and I'm calling it n. And then after that, I have the body of the function. In this case, I'm multiplying n times itself. To call that function, I go parentheses, function name, argument. Square of 5 is 25. I, of course, need some way of doing conditionals, and I'm going to use the conditional from Racket called cond, which is short for conditional, and it acts like Ruby's case statement. So I have a cond, and then the first thing is, on the first line is I have a test, and then there's some stuff to do if that test is true, and then I have a different test, and there's different stuff, and then there's an else, and there's more stuff. Very similar to the case statement. And here's a concrete example. This is calculating absolute value of x. If x is greater than 0, well, the absolute value of that is going to be itself, so I return itself. If x is equal to 0, well, the absolute value of 0 is 0, so I return 0. In all other cases, I now know that x is a negative number, so I'm going to return the negation of x to give me the positive x. Okay. The only other thing you need to know is lists. As I said, Lisp, list processor, lists. This is a list. I represent it as a set of items separated by spaces inside parentheses with a little tick in front. The tick is there because otherwise I wouldn't know if this is applying the function 1 to 2 or 3, or if this is a list 1, 2, 3. Because remember, prefix notation. This is not a function call. When you have lists, I can access the first thing in the list by calling the car. These names will come back later, I promise. That gives me the first thing in the list, or I can get cdr, which gives me the rest of the list. You might also hear me say today head and tail. I mean first and rest in those cases, or car and cdr. And I can make lists by using cons. In this case, I am consing the item 1 onto the list 2, 3, which gives me the list 1, 2, 3. Some examples. Here's factorial. We use recursion a lot in functional languages. So I have a cond. If the item I'm trying to get the factorial of is 1 or less, I return 1, because the factorial of 1 and the factorial of 0 are both 1. Otherwise, I multiply n by the factorial of n minus 1, which recursively will give me the factorial. Fibonacci. This will give me the nth Fibonacci number. So if n is less than or equal to 0, I return 0. If n is equal to 1, I return 1. Otherwise, I sum the nth minus 1th Fibonacci number and the nth minus 2th Fibonacci number. That's the definition of Fibonacci. So some of the strengths of functional programming. If I'm doing pure functional programming and I'm not modifying state at all, I don't have to worry about all of the stuff you have to worry about with concurrency and threading. Because we're not sharing memory, we're not having to lock tables, none of that stuff is even important because nobody's modifying state. Everything is just a read operation. That's really handy a lot of the time. I think that functional programs are easier to test than some of the other ones because state doesn't matter. Data in, data out, especially pure functional programs, which means that the setup for automated tests is just, this is the data I'm going to run it on. I don't have to set the state of an underlying object first. And because there's no state, you can also reuse this. I can take code that works in one program and throw it in another program, and I don't have to worry about there being context surrounding it that's required. And I really like that they're short. Functional programs tend to be really short, especially in Lisps. A lot of people hate this, but it makes me happy. So, on to our motivating example. Here's the code that makes change in Racket. And I'm going to actually slow down a little bit here, because I want to make sure that you sort of understand this. So here's the function signature. It is a function of 2 arguments. X is the amount of money I need to make change for, and denominations, is the denominations of bills and coins that are available in my cash drawer. So now I have a conditional. The first case I want to check is if the amount I'm trying to make is 0, I don't owe any change. So I can return a list that is empty, because the list I'm returning is what bills I need to pull out of the cash drawer and what coins. So how do you make change for 0? You give someone nothing, empty list. The next thing I'm going to check is, do I have any money in my cash drawer? If there are no denominations, there's no bills or coins in my cash drawer, I can't make change, so I'm going to return false. So these last 2 cases are the tricky ones. So this is the case where the amount I'm trying to make is less than that first denomination. So this is car.denoms is getting the first element of the denoms list, which is the highest bill in the cash drawer that I'm currently looking at right now. If that amount is greater than the amount of money I'm trying to make, I need to use the rest of my cash drawer. So if I'm trying to make a change for 450 with a $5 bill, I can't do that. I need to use the rest of my denominations to make change for x. So I do a recursive call. Finally, and this is the case where I actually use that first bill. So remember, I'm trying to return a list, and I make lists with cons. So I'm consing the first element of my denominations thing, which might be my $5 bill, onto the recursive call to make change for the rest of the amount, and I calculate the rest of the amount with that subtraction there. That's like that difference equals line in the Ruby. And then the same set of denominations I'm working with, because I might need 2 or 3 pennies. I might need to use the same denomination more than once. So this is the case where I don't use the current thing I'm looking at. This is the case where I do. There's really only 2 cases beyond the base. So I really, really like this. It's much shorter than the Ruby. I think it's very, very logical, and if you've got some background in number theory or mathematical theory and you're used to proofs by induction, I think the recursion looks very familiar and very comforting. But this is not actually the shortest solution to this problem that we will see today. That is given to my friend Prolog. We're going to do logic and constraint programming, and this is going to most likely be by far the most brain-breaky part of the talk. So I will try to take it slow, and you can come up and talk to me about Prolog later. I'm happy to demonstrate all this code. So I'm going to give an overview of Prolog. Prolog is based on formal logic, things like Socrates is a man, all men are mortal, therefore Socrates is mortal. So ands, ors, implications, nots, that kind of stuff. Very, very basic formal logic that's used in philosophy and mathematics and also is the basis of a lot of computer science. Prolog programs aren't made up of instructions. They're made up of facts and clauses. Yes, that's weird. And the weirdest thing about Prolog is that instead of describing the how, we're used to in programming telling the computer how to solve the problem, Prolog works different. You describe the what of the situation. One of the common examples is a logic program. So I would say, OK, the logic program says that the guy in the yellow house does not own the fish. And I would encode that. Or I would say that the guy who really likes to drink rum lives next to the man who owns the cat. And I can encode all of those facts in the system. And then what Prolog does is it uses everything that it knows, and it tries to come up with a world where all of those are true. And it fills in any blanks that are remaining once it comes up with the world where all of those facts and clauses are true. So syntax to do this is a little weird. The biggest thing is that we have variables and constants. Variables start with a capital letter. Constants don't. They start with a lowercase letter. And then we have facts. And facts end with a period. So I can say that Washington is a state, or that Washington borders Oregon, and Washington borders Idaho, and Oregon borders California. And using this, I can define a rule. And rules specify relationships between facts. So here I'm defining the rule, adjacent. And that colon minus sign is actually a logical implication. If you know what that means, that might help you understand this. But all this is saying is that x and y, now those are variables because capital letters, are adjacent if there is a fact where border x and y is true. And what Prolog is going to do with those variables is it's going to try to pattern match. It's going to go through all of the facts it has and figure out if there's some constant it can put in for x and another constant it can put in for y, or the same constant, where there's a rule that matches, or fact that matches. And this is called pattern matching, and pattern matching languages are awesome. And so here's my adjacent rule again. Now here are the facts I have, some of them, and here's the adjacent rule, and I can go into an interactive Prolog terminal and say, hey, Prolog, is Washington adjacent to Oregon? And it will say, yes. And then I can go, hey, Prolog, is Oregon adjacent to Washington? And Prolog's going to say no, because Prolog is incredibly literal. And since I only have a fact that says that Washington and Oregon share a border, not that Oregon and Washington share a border, Prolog doesn't know that the reflexive case is true for this particular rule. So I have to teach Prolog that by saying that adjacent xy implies that there's a border between xy, but adjacent xy can also imply that there is a border between y and x. I got a little tricky there. And then if I go in and say, hey, Prolog, is Oregon adjacent to Washington? Prolog will correctly say yes. And I have a couple minutes, so I'm going to go over my favorite Prolog joke. How many Prolog programmers does it take to change a light bulb? Anyone know? No. The answer to that is no. So I'm going to do some basic examples, and the canonical example in Prolog is ancestors, building a family tree. So I'm using The Simpsons, and one of my first rules is that, first facts is that father, Homer, Bart. So that's saying that Homer is Bart's father. You have to change the word order around a little bit to make it work in English. Not true in other languages that have different word order than English. You can also say that Homer is Lisa's father. You can say that Marge is Bart's mother, and Marge is Lisa's mother. So then I can go into my interactive Prolog terminal. I can start asking questions. I can say, hey, Prolog, who is Bart's mother? And that's that first line there. And what I'm actually saying is, hey, Prolog, what do I need to shove in for x? What value of x makes this statement true? And Prolog's like, Marge is Bart's mother, which is correct. And then I can say the opposite. Hey, Prolog, who is Marge the mother of? By putting the variable in a different location. And Prolog says Bart, and then I can use the semicolon to say, you got anything else? And Prolog will say Lisa. And this is the real strength of Prolog, is that I can run programs backwards and forwards, and I can put variables wherever I want. And it is crazy the first time you do this. But it's also super duper powerful. And I've showed you simple examples thus far, but you can build rules that are much more complicated. So let's build the rule sibling. So x and y are siblings if there is some z such that z is the mother of x, z is the mother of y, and x and y are not the same person, because you can't be your own sibling. And that slash equals equals is not equal in Prolog. But there's another way that you can be siblings. X and y are siblings if there is some z such that z is the father of x, z is the father of y, and again, x and y are not the same person. And Prolog's going to try to figure out whatever values it has to put into each of those capital letter variables to make this true. So I can go into the interactive Prolog terminal and say, hey, Prolog, who are siblings? And it says, oh, Bart and Lisa are siblings. Awesome. So I'm going to go into the last bit, and this is one of the most complicated bits of Prolog that we're going to talk about today. Prolog has lists, like Racket, like Ruby. I have an empty list. I have the list 1, 2, 3. I have a list apples and bananas. So I can have lists that are heterogeneous. I can have lists that have numbers or constants in them. And I can also have nested lists, which is what I'm showing on that last line. But in order to pattern match on lists, I have to have some crazy notation. This is called bar notation. I'm going to say this aloud as f bar r. You can think of the f as first and the r as rest. And this is just like the car and the cutter we saw in Racket. F is the car. It is the first element of the list. The bar separates the first element from the rest of the list, which is the cutter. And if that didn't make any sense, if I have the list 1, 2, 3, and I pattern match that against f bar r, f is going to match the 1, and r is going to match the list 2, 3. So car and cutter, same thing, crazy notation. The last little bit is this is an underscore. So I might break some of your brains, I hope not, but did y'all know that you can use the underscore to say, I don't care about this variable, it's unused in Ruby? And then good, people are nodding, this is fantastic. I've broken people's brain with that one before. Racket has the same thing, and underscore in Racket is called meh. I like that. Learned that from Ryan Davis last night. And then in Prolog texts, we refer to this underscore as don't care, which is this variable isn't actually used for any of the logic, so put whatever you want there. I don't care. So we're going to do a quick list function. List rule, not a function, not in a functional language. So this is member. It's like include question mark in Ruby. So x is a member of the list. First argument is the thing I'm looking for. The second argument is the list. X is a member of this list if x is the first thing in that list. Makes sense, right? That's one case. Forgot to change the bold. The second line, x is a member of this list if I don't care about the first thing, doesn't match, but x is a member of the rest of the list. So x is a member of this list implies that x must be a member of the rest of the list. So recursion, it's handy that way. So strengths. One of the awesome things about Prolog is that thing I mentioned about running programs backwards and forwards. This is true of logic programming in general. There's a great talk about Minicanren where they actually run their logic system backwards to generate the code for factorial. Because why not? You can run it backwards and forwards as long as you set up the constraints correctly. One of the early use cases of Prolog that I've read about was actually scheduling time to use limited resources in a research lab. I believe the resource was a dolphin, and they needed to figure out how to work everyone's schedules around, like this experiment's going to take 45 minutes, and we need to repeat it every 3 days for a month, and I have class at this time and all that. They used Prolog to put all those constraints in and solve the problem so that they had a reasonable shift schedule. So, time to make some change. So, we're in Prolog. The weirdest thing, and the thing that always gets me when I have to context switch into this language, is I don't have return. There is no concept of a return. Everything is encoded in the method signature. And you have to have that so you can run it backwards. So, we're going to have a change rule. It has 3 arguments. The first is the amount. The second is a list of coins or bills we have. And the third is how you make change for that amount using those bills, that list of coins. First one is an integer. The second 2 are lists. So this is going to be true only if change, that last argument, is how you make change for the first amount using the coins in the middle. I think it might have just snapped for a couple people. This is weird. So here's the code for the change function. It's actually shorter than the racket. We'll go through it, I promise, I promise. So first case, the easy case. How do I make change for the amount 0? Well, change for the amount 0 is the empty list. And I don't care what's in my cache drawer, which is why I'm using the underscore, because I don't need to know, don't need to use anything from the cache drawer if I'm making change for 0. That's the easy one. Here's the second one. Focus just on the first line right now. This is where we use pattern matching. So I've got an amount A, and this is saying that I make change for the amount A by using the first thing from my cache drawer, and that is the first thing in the way I make change. So this is the case where I use that first bill or coin in the cache drawer. And I can only do that if the amount is greater than the denomination of that first thing. And if those 2 things are true, I need to calculate B such that that is the difference between the amount, that is what's left over after I use that bill. And the other thing that has to be true in that case is that I can make change for B using the same stuff in my cache drawer, and the way I do that is X, which matches that X on the very top there. So A is greater than F. I can use this because the bill is smaller than the amount I'm making. B is equal to that difference, the remaining amount of change. And the way I make change for B is X, which matches on that top part. And remember, Prolog is going to make all of the instances of each variable the same thing. So that's the second clause. Third clause, this is the case where we don't use the first coin or bill. So I used a don't care again. I only want to apply this one if I'm actually making more than 0 in change, because if I'm making just 0, I can use the first one above, the very first one. And in this case, I'm going to say, hey, the way you make change for A is you use the rest of the stuff in your cache drawer, and the way you do that is X. So this is the other recursive case. And I promise it works. And you're probably going, ow, my brain right now. I love Prolog, and this was the hardest of the examples for this talk to write. I actually had to break into the debugger to do it. And I didn't have to do that for even what's coming next, which is procedural. And we're going to do that with assembly. So the fact that I was able to write the assembly without the debugger and I needed the debugger for the prologue is hard. So assembly is old school programming. We have a limited vocabulary, a limited standard library, a limited number of functions we can call. And by limited, I mean very limited. For the assembly I'm using, I think there are less than 30. I think there's like 22. And there are tons of assemblies that exist. I am using the assembly from a book called, well, it's commonly referred to as NAND to Tetris. I have a link, I have a bibliography entry for it in NAND, so you can grab it and check it out yourself. The reason I'm using this is that it is less ugly than most assemblies. It looks more like the programming you're used to, and it's very, very simple. So here's the syntax. So the big thing about the assembly is that I have 2 registers, A and D, and those are the only 2 things that I can do operations on. D is D because it is the data register. A is A because it could be a data register, or it can be the address register. And when it's the address register, I use whatever value is in A, and I go pull that cell out of memory. So in the cases where I'm using A to access memory, I'm going to actually just call it M. So I'm going to use A, D, and M, but I only have 2. It's just when I'm using M, I'm using what A is pointing to, And when I'm using A, I'm using the actual value of A. And circling back to Racket, we had car and cdr. Car stands for the contents of the A register. Cdr stands for the contents of the D register. That's where the names came from. So we got some computations. I can do A plus D. I can do D minus A. I can do A minus D. I can do A plus 1 or D plus 1. I can do A minus 1 or D minus 1. I have a bitwise not, a bitwise and a bitwise or. And I can negate A or D. And any place I use A, I can also use M. So like M plus 1 or D plus M. And that's it. That is the contents of the list of things I can do. And important to note, I don't have multiplication, don't have division, don't have anything that even remotely looks like a list. Very, very limited. But I can actually assign the things I calculate to values. So I can assign to any of the registers or to memory. So I can say D equals M plus 1 or D equals D minus 1. And I can also do multiple assignment. So I can say M and D both get the value of A plus 1, which is crazy because then I'm incrementing the memory register. Yeah, that's a bad idea. I need to be able to get constants into my program. And the way I do that with this @ syntax, and constants only can go into the A register. That's why it's @. So if I want to load 100, I do @100. If I want to have, I can have a label. And I use this label somewhere in the program to access the line of my program that this label is on. And it, again, since it's an @ goes into the A register. And I use this for jumps. Jumps are of this format. There's a value, a semicolon, and then the type of jump. And so I'm like, the value in this case, in this example is D. JGT is jump greater than, and I will jump to whatever line of the program is in the A register if D is greater than 0. I don't get to have any other greater thans. It's always in reference to 0. So I have JEQ, jump if equal. And so this will always jump because I'm jumping if 0 is equal to 0. Jump greater than, jump less than, jump greater than or equal to, jump less than or equal to. I also have a non-conditional jump, which is JMP. So those are the jumps I have. Those are the only form of branching logic I have in this entire language. So here's how we add. This loads a 2 into the A register. I then move the contents of the A register to the D register. This loads a 3 into the A register. And I add what's in my D register to my A register and assign it to myself. And then I take whatever is there and I assign it to the contents of memory cell 0. And it's memory cell 0 because I put a 0 into the A register, and then I'm using an M, which means it refers to memory, not to the value in A. See, it's easy. Here's how I sum the digits from 1 to 5. I'm actually doing it backwards. So the first thing I do is I'm going to store them. I'm going to store my result in memory cell 0. So I want to zero out memory cell 0. And then I'm going to store 5 in memory cell 1. So I load it into A, assign it to D, and then load address 1 into A, and then assign whatever is in D, which is 5, to memory cell that's referenced by the address in A, which is 1, so putting in memory cell 1. Here's my loop. The parentheses notation is a label. First thing I do is I pull whatever is in memory cell 1, which is 5 in this case, and I put that in D. And then I'm going to take whatever I have in D and add it to the contents of memory cell 0, which is my accumulator. So now it's memory cell 0 is 5 and memory cell 1 is 5. And then I'm going to take the contents of memory cell 1 and I'm going to subtract 1 from that. So now I've decremented to 4. And I'm going to store that in both back in my memory cell 1 and in D. And then I'm going to do my logic. And here's my loop. So I'm going to load end into my A register. This is where I want to go. And it's the end of my program if my program's over. And I know my program's over when my counter has gone from 5 to 4 to 3 to 2 to 1 to 0. And so if D is less than or equal to 0, I'm going to jump to the end. Otherwise, I fall through to my loop label, and I'm going to go back to the top of my loop in all other cases, because I have an unconditional jump there. Awesome. So strengths. There are no strengths. I don't have use for assembly on a daily basis. I'm really hoping that none of you do too. But procedural style in and of itself can be useful. And you can write procedural style in any language. Most of us, our very first program was procedural. Hello World is totally procedural. All of the scripting stuff we write is generally procedural. Do this thing, then do this thing, then do this last thing. And writing procedural code is generally pretty easy. For most of us, our brains instinctively think this way. So here's making change in assembly. So I don't have lists. So I'm going to use memory 0 for the amount to make. I'm going to use memories 1 through 4 for my coin denominations, 25, 10, 5, and 1. And I'm going to use memories 5 through 8 for the number of each coin to use, because I have memory. We'll turn it into a list. The assembly I'm using doesn't understand this M syntax. It uses R instead, so you'll see this in the code. So this loads 67 into memory register 0. And then, and then this loads the denominations. And then this is the code for quarters. So I load in the amount I want to make. I load in the amount that a quarter is. I subtract the amount that a quarter is from the amount I want to make. If the result is negative, I don't need it in quarters, so I go on to dimes. If the result isn't negative, I save the amount I have left, increment the number of quarters I've used, and go back to the top. So I didn't cover anything in detail, and I've got 4 minutes left according to my timer, so let's do this thing. So here's where you can learn more about functional. Talks by Jim Weirich, including his Why Not Adventures in Functional Programming keynote from RubyConf 2012. Again, I tweeted the slides, so you don't have to take pictures of this. The slides are online. And then Friedman and Fliesen have the Little Schemer, the Reason Schemer, and the Season Schemer. Those are fantastic books. They're written in Socratic dialogue. They're awesome. And the Structure and Interpretation of Computer Programs is a very large textbook on the fundamentals of computer science from a functional perspective. I gave a talk at Cascadia Ruby 2012 on Prolog. It's the 45-minute version and much easier to follow than this talk. There's also the Art of Prolog, Cause and Effect, the Prolog Programming for the Working Programmer, and Prolog Programming for Artificial Intelligence. And then I mentioned the assembly I used was from a book called Nanda Tetris. The actual title of the book is The Elements of Computing System, Building a Modern Computer from First Principles. I highly recommend, if you don't understand how your wizard box works, you follow this book. You start with logic gates and you end up writing a very small version of Java, including the assembler, the machine code, and the VM underneath. It's awesome. And if you just like languages, 7 Languages in 7 Weeks is the classic. And then I also have, and it's actually in my bag, a book called Exercises in Programming Style, which is basically this talk, but in book form and better. It goes over lots of different styles and how to do the same program in lots of different languages. I have it with me. Come find me, and you can flip through it. So I'm supposed to have a thoughtful closing here, but I'm out of time because I used every last second I had available. And I also kind of told you what the whole purpose of this talk was up front. You can learn other programming languages. Other paradigms are not that different. Everything has conditionals, accessing memory, integers, mathematics. It's all similar. So go learn other languages. Because it's me, I have dinosaurs. You can come get one later. There's a bunch on a chair up front. And I have special edition Mardi Gras dinosaurs for RubyConf New Orleans. I also have Google Cloud stickers, and I'm done. See you.